Right. We're going to talk about this part. See here. Now, you should have seen these optical fibers, right? Now, if you know that if your internet connection is given through these optical fibers, your connection has to be very fast, right? So most of the time, your router is a optical fiber router. So then the signals are transmitted all around the connection through the optic fibers, fiber optics, right? So then the transmission speed is extremely fast, right? So then these the speciality in these optical fibers. Now, if you just imagine, right, when you talk about, just imagine a situation like this, right? Now, just think of a stomach, right? Think of a stomach, okay? Right? You are imagining our stomach. Now, this stomach has gastritis condition, and then you have like all sort of these what do you call damaged epithelium, right? And then if you want to observe this damaged part of the stomach, like since we can't like now our stomach is somewhere around, somewhere in the stomach, somewhere in the abdominal region, and if you want to send light to observe the inside structure of the stomach, that would be difficult. If you know, like if you know, uh, that's because like you have your buccal cavity over here, head, eyes, nose, and then the buccal cavity over here, right? Methylene gila, you will have all these bends and all of these things, and then only you will reach to your stomach, right? So you have all these bends. As you all know, light travels always in straight lines. Okay, light always travels in straight lines. So you have many bends, many bends until you reach your stomach. There will be a difficulty to see the things inside the stomach by using a light, right? So for the as a solution for this, the scientists invented optical fibers. The specialty in optical fibers is uh, the light undergo total internal reflection. Now, there's another example. If you have a tube like this, right? If you have a tube like this, you can definitely send light through this. If you have a light source like this, you can send light through this directly onto the other side. You can clearly see because light travels in straight lines. But if you have a bent tube like this, okay, if you have a bent tube like this, so if you observe from here, if there was a light source from on this side, right, you'll never be able to observe this light because light cannot go uh, in this through this bends, right? So this so because of that, you will be finding difficulty to check the things inside the stomach, right? So because of that, the scientists invented something called optic fibers, right? The speciality in this is the inside the optic fibers, fiber optics, total internal reflection take place, right? So optical fibers are most of the time made up of plastic or from glass, right? Made from plastic or glass. So what really happens when light travel through them is the light subjects into total internal reflection, right? If you're watching it from here, if you are the observer, if a light ray enters this optic fiber from here, the light would get totally internal reflected again like this. So because of that, this light ray gets the capability to travel through even these bends, right? So if you insert such an optic fiber into your stomach, it doesn't matter how much the pathway of the light bends, because of this total internal reflection, the required place could be illuminated with light, right? So if you it doesn't matter how many times the optic fiber bends, but the required place could be illuminated because light traveling through the optic fiber subjects into total internal reflection, because of that light could be even sent through these bends, okay, right? So this is one option, one application of this optic fibers where total internal reflection is being used, right? And the same optical fibers, through the same optical fibers, we send these telecommunication signals in the form of light, right? So in your mobile phone routers, not mobile phone routers, in your internet routers, so these telecommunication signals are sent through these optical fibers as a light signal, right? So though they bend, right? Though they have long distances, no problem, but the communication will be very fast, right? That's why your route speed is very fast if you have a fiber optics router, right? So what you have to understand basically how the light would travel under total internal reflection through optical fibers, right? This is what you have to understand. So I think that you should have seen all of these things. Have you seen this kuru wage thing, like when you have a light source from this end, right, this light travels through these optical fibers until to the end, right? So these are the optical fibers. Now this equipment which is made using these optical fiber is called endoscopes. There are different endoscopes used for different purposes to observe inside the body, without doing an open surgery, right? If you want to observe, now sometimes if you wanted to observe something inside, you may sometimes need to open up and see what's inside. So without going to such a step, you could easily use an endoscope with a camera and a light, and then you could see what's inside and what's the condition inside of your structure, uh, only by using this endoscope with optical fibers, right? So what practically uses in that, there is total internal reflection of light, right? Can Upeka read it for me very quickly?
Yes, sir. Optical fibers are flexible, transparent fiber made of glass or plastic.
Right, that's very important. You have to highlight it. It's made of glass or plastic, right?
Light rays that enter through one end of the optical fiber travel through the fiber while undergoing total internal reflection and leave the fiber through the other end.
Right, that's also important. So through these optical fibers, total internal reflection takes place, right? Okay, great. Next one.
Even if the fiber is many kilometers long, light will leave it without a significant
loss of intensity.
The instrument called endoscope, which is used to observe the internal organs of a human body, makes use of optical fibers.
Okay, that's very important. Endoscopes are made using optical fibers, right? So just highlight endoscopes. That's enough, right? Okay, next one.
Optical fibers are used to provide internet connections and for decorations.
Okay, right. Then that's great. So we are going to few other situations where the total internal reflection is taking place. Okay, now you need to use the knowledge what we discussed, what we actually got on the last day, right? So here think, right, now see here we have a glass prism. Okay, we have a glass prism and you need to answer me for some of my questions, right? Okay, right, you have a glass prism like this. Now tell me, I think you could understand that is a right angle glass prism. If the prism is like this, the angle over here should be 45 degrees and 45 degrees. Do you agree with me for this? If you guys agree with me for this, you can put up your hands quickly. Okay, Ellie, what about you? Susan? Susan? Susan, are you there? Okay, response current. Right, Vincent, now there is a light ray. Now, what can you understand? This is glass, okay? This is glass. The glass prism is obviously made up of glass, and this is air, okay? And this is also air. Now, this is on a table. We have placed a glass prism, okay? Right, now, Vincent, imagine that there's a light ray coming through, okay? I hope you can remember the critical angle of glass. Critical angle of glass is what? It's actually 42 degrees, 42 degrees, right? Critical angle of glass is 42 degrees. Hope you can remember it, right? And then there is this light ray, Vincent, entering the glass like this. Can you see that the light ray touches the interference, the border between glass and air perpendicularly? Can you see that? Bhimsen, I'm going to ask the question from you. Can you see this?
Yes.
All right. So then now tell me, how would the light ray behave? What would happen to the light ray?
Same
How
path.
would it? Yeah, okay. It will enter the medium of glass without any refraction, is it? because it's touching the interference perpendicularly, there will be no refraction. It will just enter the glass. Okay, it just enter the glass. Okay, without any refraction. If there was a refraction, the pathway of the light ray has to be changed. It did not change because why? The glass was intercepted. Glass was touched. The medium, the border between the two transparent media was touched perpendicularly. There's no refraction take place. Okay, now this is the way how the light ray goes. Okay, now this is the point of incidence. Okay, now this is earlier this was the point of incidence. It entered the glass without any refraction because the light ray incident on the interference perpendicularly, and then next situation, this is the point of incidence. Okay, right, now that is the point of incidence. Now what has become the interference? This has become the interference, air and glass. This is air again, this is glass, and this is the interference. Now I'm going to make a my construction, do my construction for the normal. So what is the condition when you're constructing the normal? Normal has to be constructed in a way that it is perpendicular to the interference. So now in this condition, this is the point of incidence and this is the interference. So I have to construct my normal in a way that my normal is perpendicular to the hold on. Right, my normal is perpendicular to the interference. Okay, I did it. Right, my normal is now perpendicular with the interference. Right. So then, my normal is perpendicular with the interference. Okay, done. My normal is perpendicular with the interference. And now what should I consider as the incident angle? This has to be considered as the incident angle, this one, because the angle in between the incident ray and the normal, right? The yellow ray is the incident ray and this is the normal, this is the incident angle. Now can somebody tell me what would be the value of I? Can somebody tell me? Vincent,
45.
can you tell? Yeah, exactly. No? It's 45. It's 45. Elisha, can you understand? Upe, can you understand that the angle is 45? Eli, Upe, can you understand that the angle is 45? Why? Now, since I have drawn my normal perpendicular with the interference, this has to be perpendicular with the interference. It has to be perpendicular with the interference. So on this side also, this normal has to be perpendicular with the interference. Okay, it has to be perpendicular. If it is perpendicular, can you see that the perpendicular line is being equally divided by this? Now if it is not that, if you can go for further explanations, like if it is 45, this has to be for 90 degree, and the total internal angle of a triangle has to be 45, and then this has to be again 45. So this one 45 and this one has to be 45 in order to make a perpendicular. So there are different ways how to obtain that as a 45-degree angle. So this is basically maths. So if you can understand this is 45 degrees, that's great. So this incident angle has to be what? Incident angle is 45 degrees according to math. Okay, right? So this incident angle is 45. Now in this situation, Vincent, my incident angle is incident angle which is 45 degree is greater than the critical angle of glass which is 43, 42. Can you understand, Vincent, that? Vincent, can you understand that? In
Yes,
this
sir.
situation, my incident angle is 45, which is greater than the critical angle of glass. Now, if such a situation take place, now tell me from the previous day knowledge, would the light ray enter into air or would it get reflect back into the same medium if the incident angle is greater than the critical angle of the particular medium? Does the light ray enter into the next medium or does it get reflect back again to the same medium?
Get reflected to the same medium.
Reflect back to the same medium. So now this light ray gets reflected back again into the same medium because now the incident angle has been exceeded. Incident angle is greater than the critical angle of glass. So the light ray gets reflected back again into the same pathway. Now, Vincent, here the light ray again touching the interference between glass and air perpendicularly. What will happen to the light ray? Gets refracted or gets entered into the second medium without any refraction.
No refraction.
No refraction. Okay. So now tell me overall, this light ray after traveling through this glass prism, it has turned. So up to which sort of which sort of an angle it has been totally turned? How much of a turn it has been made after traveling through this glass prism? So 45 here and 45 here, isn't it? Right? Because it has to be also a perpendicular here on this side. So it has turned all together 90 degrees. Can you understand? So it has traveled in this way and it has taken a 90 degrees. So if you place a glass prism like this, a light ray could be turned with a 90-degree angle. So here what actually work here is a total internal reflection. Here is the place where total internal reflection takes place. Did you understand that, Upeka?
Yes, sir.
Okay. Eli, was it clear to you? Emily, was it clear to you?
Yes, sir.
Okay, perfect. Right. Next part. So you don't want to write anything. I just explain what is just given over here. So keep it in your mind how the light ray get reflected. This is how it is happening. Okay. So there's another situation. There's another situation. It's like this. In the next situation, what do we do here? We place the triangle on the other way. Okay. We place the triangle on the other way. So it's actually like this. Okay. Okay. It's like this. Triangle is something like this. Right. Okay, now you need to answer me. Okay. So still the critical angle of glass, that's 45. Sorry, 42. Still that is there, right? It's 42. 42 degrees. Okay. Now, Upe, now tell me if this is the 90-degree angle is, right? This is the 90-degree angle is. Okay. So this has to be 45. This has to be 45. Okay. Upe, now tell me, there's this light ray trying to enter the glass. This is air, right? This is glass. This is again air, right? This light ray tries to enter the glass. Okay, right. Now tell me, how does it incident on the glass interference? Glass interference. Upe, you need to answer quickly.
Sir, what's the question again?
How does the light ray touches the interference? With an angle or perpendicularly?
Perpendicular.
So then would it get refracted or just enter the second medium without refraction?
It will enter the second medium.
Without refraction. Okay, entered. Now this is right. Enter the second medium without. This is the point of incident, isn't it, Upe?
Yes, sir.
And this is the now I'm constructing the perpendicular. Sorry, I'm constructing the normal. I have to construct normal through the point of incidence in a way that it is perpendicular to the interference. Now my normal is perpendicular to the interference. Am I correct?
Yes, sir.
Okay, perfect. So this angle, what do you call this angle between the between the normal and the incident ray? What do you call this angle?
Incident angle.
And what would be the magnitude of that angle?
45.
45, right? So then in this situation, my incident angle is 45. My incident angle is 45, which is greater than the critical angle of glass, which is 42. So what would happen? This light ray enters the second medium or not?
No, sir.
So what would happen to that light ray? Gets reflected back into the same medium, isn't it?
Yes, sir.
Got reflected. All right. Now the situation is, this is the point of incidence. Are you clear?
Yes, sir.
And I have to construct the normal again. Now point of incidence in a way that it is perpendicular perpendicular to the interference. I constructed the normal. Okay. Now this angle between the normal and the incident ray, what is it?
Angle of incidence.
I know. What is the magnitude of it?
45.
45. It's again 45. Now would it enter the second medium?
No, sir.
Because again my incident angle has exceeded the critical angle of glass, isn't it? It has exceeded the critical angle of glass, which is 42. Now what would happen? The light ray would get reflected back again. Okay. Now it's touching the interference perpendicularly. What would happen to it? Without the refraction, enters back into air. Now tell me, Upe, with how much of a magnitude the light ray has turned?
90 degrees.
Into 2, right? See here,
Yeah.
it was to travel on to this path and it has turned completely back onto this path. So how much of a turn?
180.
180, isn't it? So if you keep a prism, glass prism like this, the light ray could be turned 180 degrees. Ili, was it okay to you?
Yes, okay.
Yeah, Vincent, how was it to you?
Okay, sir.
Right, Emily?
Okay, sir.
All right, right. Okay, so then we are trying to talk about lenses now, right? So what you have to know about these lenses are also optical instruments, right? Optical equipment. So far we have discussed about reflecting surfaces, okay? So we discussed one of those reflecting surfaces as a plane mirror. Plane mirror is a reflecting surface. Concave mirror is a reflecting surface. Convex mirror is a reflecting surface. What would happen to these? What will happen to the light rays fall on these reflecting surfaces? The light ray could get reflected back into the same medium where from this light rays came into these reflecting surfaces. In no situation light could travel through these reflecting surfaces. The light ray strikes on the reflecting surfaces and gets reflected back into the same medium where they came from. But when you talk about these lenses, actually through lenses light can pass through. Actually there are two types of lenses. We will be talking about concave and convex lenses. This is actually a convex lens, right? Convex lens, you have spoken about all of these when you all small, right? This is a convex lens and this is a concave lens, right? Concave lens is something like this. Actually what happens to the light rays when light rays try to travel through them. Light rays try to travel through them. So if you clearly see, when the light rays are trying to travel through them, they have traveled through different media. Why do you say like that? This is air. This is glass or plastic from what the lens is made, and this is again air. Okay. So when a light ray travels through such a lens, the light ray can't travel in the same pathway where it was trying to travel because it's entering into a different transparent medium with a different density, different particle distribution. So then the pathway of the light rays would definitely change when the light rays are traveling through these lenses. Only thing what you have to understand is when you have a reflecting surface like a plane mirror, concave mirror, and convex mirror, the light rays would get reflected back into the same medium where the light rays came from. But when you're talking about these lenses, actually the light rays go through the lenses. So the situation when a light ray tries to go through the lens, light rays have to travel through different transparent media like air, glass, air, plastic, air. Right. So as a result of that, light rays would change their pathway. That means simply the light rays would get subjected into refraction when they are traveling through lenses. Are we guys clear up to that? I just made a simple explanation. Put up your hands if you understand that part. What would happen to the light rays when when these light rays traveling through the lenses? Actually, light rays travel through the lenses, huh? And they get subjected into refraction. Can you understand that part? Put up your hands, please, if you could understand that part. Eli, was it clear to you? Right. All right. Emily, do you know how to put up your hands? Oh, you have a problem in keep raising up your hand. Emily, දන්නව නේද මෙතන තියෙන right, okay, හොයාගත්තා. All right, great. Okay, Upe, can you read it for me about the lenses quickly?
Yes. A lens is an optical device with curved surfaces made of glass, plastic, or any other transparent material.
All right.
A lens alters the path of light rays that pass through it by refraction. Images on the retina of our eye are formed
by a lens. Okay, now tell me, what do you have as a lens in your eye? what sort of lens? I mentioned two types. What lens do you have? I'm asking about your eye lens, a natural eye lens, which is made up of different types of proteins. Your eye lens is, guys, your eye lens is a convex lens. So you have your eyeball like this, You have a region called retina, which is a very sensitive area for light. So when light falls onto your eye, the light which is falling onto your eye will be converged and focused exactly on the retina for you to see different objects, for you to see different things, right? So your eye, naturally, your eye has a convex lens. It has the capability of focusing. It has the capability of converging light rays falls onto the eye and focusing them sharply on the retina, right? So we have a convex lens. So within brackets in front of retina, right? A convex lens. Retina is in front of uh, yeah, image of the formed by a lens in within bracket, right? A convex lens, right? Eye has a convex lens, right? Next part.
Lenses are used in telescopes and binoculars, which are instruments that help us to see faraway objects clearly. Lenses are also used in microscope, the instrument that allows us to see very small objects that are not visible to the naked eye. Magnifying glass or simple microscope that magnifies small objects is also a lens.
In this magnifying glass or simple microscope is the hand lens, within brackets, right? Hand lens. Okay, now I have a question to ask from you. Okay, right, guys, this is the thing. Okay, right, when we talk about these optical instruments like telescopes, binoculars, and then about this microscope. Now, people feel it like this. People, in the sense, are students, right? Now, now they think like this: like when the objects get away from you, the objects become smaller. Okay, when the objects gets away from you, the objects become small. I'll tell you what the reason for that. Okay, so then first of all, I have to tell you the far point of your eye. What do you think the maximum distance that your eye can see? Quickly get me some answers. What do you think the maximum distance that your eye can see? Right, Bima? I just need some rough answers. What do you think the maximum distance that your eye can see? Okay.
As far as the light ray can go.
As far as the light ray can go. Okay. What else? Upe, Eli, Tagala mic on karak ya? Yeah, Upe, what do you think?
I'm not sure.
Okay, Eli, what about you? Hey, I will just come up with a condition saying that no civil answer could be given. Nah? Right, okay. Emily, what about you? Emily, infinity Emily there. Were you there for the class on that day, Emily? Yeah, infinity, true. It's infinity, yeah. It's like this, okay? Right. Now, why do the okay? It's like this. Why do the light? Okay, it's like this. So you have your eye like this, okay? You have your eye like this, okay? All right, I will draw the correct eye. See here, that's just important part for you all to learn this, right? So you have the convex lens, and then your eyeball, okay? So now just imagine. Now, basically, when light falls onto your eye from a distant object, light comes into your eye as a parallel light ray. When light falls onto your eyes from a distant object, light comes as parallel rays. Okay. Now, just imagine there's an object over here which is this much of a size, and from that object, this is far away. Just imagine from this object there are two light rays reaches your eye. These two light rays gets actually converged, right? Gets converged and gets focused on the retina. Okay, and then this will create some sort of an angle on your retina, saying the two edges of the object, and this angle what's create. Now, depending on the edges, only know the light rays would come and gets converged. So, due to this angle created on your retina, you will have an idea about what size of that object is. Okay. Now that's what tell you the 2 points, the 2 edges, not the 2 edges, overall edges from every edge the light rays comes. So this angle creating on your eyes, for your simple understanding, this angle creates on your eye tells you how much would be the size of this object. Okay. Now, as you all know, you should have heard when the two parallel lines goes to the infinity. Now, don't think about the things what you have heard. Now, just think about two rails, right? Two rails. If you see them that they are going far away from you, what will happen to the two rails? They'll be like getting closer to each other. Have you seen this? Even when you draw these rails in your diagrams, in your pictures for art, you do the same, right? These rails appears to be meeting each other. So the two parallel lines, we assume that they're meeting at the infinity. Okay. So now if you just assume that there's a light ray coming to your eye from a very distant place, if you imagine that there's a light ray coming to your eye from a very distant place, okay. Now these two light rays were parallel because they were not so distant. These two light rays were coming from an object which was distant but not so distant, not so far away but somewhere close, right? But if you think about an object which is actually at a very distant place, somewhere at very far away, so the light rays coming from that object, would reach the eye. They will reach the eye, but as a single light ray, or mostly like closely arranged two light rays, right? So these right, see here, right? Now from the object which is very far away, parallel light rays they appear to be meeting with each other. Light rays when they get converged into your eye, the angle created on your retina would be not that differentiated, would be not that recognized. So because of that, you will not be able to see the size of the image at all, right? So it's not because your disability of your eye, it's because that the object is too far away, and this light rays reaching your eye is reaching your eye as a single ray because of the distance. Because of the distance, the light ray reaching your eye reaches your eye as a single ray. So then because of that, there will be no differentiation. There will be no differentiation in your retina to recognize such a considerable angle. That's why you can't see the object which are far away. So what do we do? So are we when we want to still now because light take is light in a light when because they are too far in a light rays, parallel light rays had to reach from a single light ray. Parallel light rays they appear to be meeting each other, overlapping each other. So the object take a parallel light ray reach like a single light ray. So එතකොට parallel light rays දෙක අතර තියෙන angle එක consider කරගන්න බැරි වෙනවා මෙතන එකට අපේ ඇහැට. So then we don't see the object. So when we want to really see this object, what do? Are we bringing the object near our eye? We can't do that. What do? We use some optical instrument like lenses. දැන් අපි මොකද කරන්නේ? දානවා මෙතෙන්ට මෙන්න මේ වගේ convex lens එකක්. Sorry, concave lens එකක්. එතකොට concave lens එකෙන් මේ light ray එක diverge කරලා දෙනවා මෙන්න මෙහෙම. කොහොම ඩයිවර්ජ් කරලා අපේ ඇහැට දෙනවා. දුන්නාම ඇහැට පුළුවන් ඔන්න දැන් බලා ගන්න. දැන් පේන ඔබ්ජෙක්ට් එක ලොකු වෙලා. අර ඔබ්ජෙක්ට් එක we did magnify, but what happens before reaching our eye, before reaching this light rays into our eye as a single ray, අපි concave lens එකක් දාලා light එක ඩයිවර්ජ් කරා. ඩයිවර්ජ් කරපු light එක ඇහැට දුන්නා. දැන් ලොකු angle එකකින් ඇහි create වෙනවා image එක, right? So what do we do? What do we really do? We make these light rays diverged and reach our eye in a way that it could create a considerable angle for us to see it. Then අපේ ඇහැට මුකුත් කළේ නැහැ. අර ඔබ්ජෙක්ට් එක ළඟ ගෙනාවෙත් නැහැ. අර ඔබ්ජෙක්ට් එකේ ඉඳන් ලයිට් රේස් මොකද කරේ? ඩයිවර්ජ් කරලා අපේ ඇහැට ගත්තා. එතකොට මේ ඔබ්ජෙක්ට් එකක් ඉන්ෆිනිටි එකේ තිබ්බත් if it emits light ඒ එන ලයිට් රේ එකක් අපිට පුළුවන් වුණොත් considerable amount එකකින් ඩයිවර්ජ් කරලා අපේ ඇහැට දෙන්න we could see the object. So the maximum distance that we can see through our eyes is infinity. And some objects pain because the objects when they get far away from us, ඒගොල්ලන්ගෙන් ඉඳලා එන light rays two parallel light rays විදිහට reach කරන්නේ අපිට ඒවා single light ray එකක් විදිහට reach කරන්න. එතකොට තමයි අපිට object එකක් තියෙනවා කියලා recognize කරගන්න බැරි වෙන්නේ because the angle created by these two light rays on the retina will not be enough, right? Considerably it will not be enough for us to understand that there is an object, right? So අපි මොකද කරන්නේ? අපි ඇහැට මුකුත් කරන්නේත් නැහැ, object එක ළඟට ගේන්නෙත් නැහැ. අපි ඇහැ ඉස්සරහින් optical instrument එකක් use කරලා ඒ light එක diverge කරලා then focuses on the retina. That's what we simply do. So our far point of the eye is infinity. So without your eye being stressed, eye එක stress වෙන්නේ නැතුව එක දිගට ඕන දෙයක් දිහා බලන් ඉන්න පුළුවන් ළඟම point එක near point එක that's considered to be around 25 centimeters, right? 25 centimeters, right? So then මට කියන්න ඕනේ ඕක නෙමෙයි. So when we talk about these two things, what do you think? දැන් ඕගොල්ලෝ සමහර කට්ටිය හිතන් ඉන්නවා, සමහර ළමයි හිතන් ඉන්නවා දැන් මේ the distant objects, they can't be seen because they're very small. They can't be seen because they're very small. ඒක magnify කරලා වෙන්න ඇති අපි බලනවා. එහෙනම් the microscope also does the same. It can magnify the small thing. So microscope එකකිනුත් ඈත තියෙන දේවල් බලන්න පුළුවන්. So you can't. Actually microscope does something else. Microscope එකකින් ඇත්තටම තියෙන size එකට වඩා ලොකු image එකක් හදලා දෙන්නේ. අර ඈත තියෙන object එක බලන්න ඒකට වඩා ලොකු image එකක් හදලා හරියන්නේ නැහැ. ඔයා කරන්න ඕනේ object එකේ image එක අපේ ඇහැට ළඟට ගෙනල්ලා දෙන එක. මෙන්න මේ වගේ වැඩක් කරන්න. So that could be only done by binoculars and telescopes, not by microscopes, right? So hand lens, simple microscope කියලා කියන්නේ අර Sherlock Holmes ගාවෙම තියෙන ළමයි. මෙන්න මේ වගේ උඹලා use කරලා තියෙනනේ hand lens එක මෙන්න මේක. So what simply it is, it's a convex lens with a hand. It's a convex lens with a hand, right? Okay. So that is it about them, and then we are moving into the next part, right? Okay. So we have a classification of lenses, mainly concave and convex lenses, converging and diverging lenses we call them, and they have different shapes and different characteristics also. We're not going to talk about all of them. We will be simply talking about biconvex, which is this, right? Which is this, and biconcave, which is this. Two lenses. Okay, that's only about it, right? So then how this convex lens is made, right? I'll just explain it and then we can read it, right? So I hope you can remember how these mirrors were made. Convex and concave mirrors were made in a similar way that we have to make this convex lens. Okay, it's convex, I think. Yeah, convex lens. Yes. Now in this situation, guys, see here, I will take two spheres, glass spheres. I'll take two glass spheres. Okay, this is one glass sphere. Okay, make glass sphere center point. I'll mark it as C1. Okay, this glass sphere center point is C1, and then I'll take another glass sphere. All right, a glass sphere center point this one. Okay, hold on. A glass sphere center point this one, which is called the C2. All right. Now I'm asking this thing, okay? Answer me. Elisha, from the center point, if I draw a line like this, from the center point, if I draw a line like this, what do you mathematically call that line? From the center point, if I draw a line to the circumference of this, now what you have to understand, this surface, this curved surface, this curved surface was obtained from this sphere, which has a center point called C1. Okay, then this curved surface, the The blue curved surface was obtained from this sphere, glass sphere, which has a center point C2. So then what do I do here? I simply draw a line from this C1 point into the circumference of this circumference of the curved surface, circumference of the circle. Okay. So what do you mathematically call it?
Radius.
Radius. Can you remember when I was talking to you about mirrors, I told you that the radius touches the circumference perpendicularly. Can you remember that, Telly?
Yes.
Yeah. And then if I draw a line like this, what do you call that, Telly, again? From this C2, I'm drawing a line like this to the circumference of its circumference. What do you call that in mathematics?
So that's also radius.
Radius. And according to the things what we have learned, that radius also touches the circumference perpendicularly. Can you understand that?
Yes, sir.
Right. So this is to be considered as the principal axis of the convex lens. I hope you can remember when we were talking about the curved mirrors, concave and convex mirrors, we had a principal axis. Can you remember? Right, we had a principal axis. If you could remember, right. If you could remember, we had a principal axis when we were talking about this curved mirrors. This is the curved mirror. This is the principal axis. And I said you this principal axis touches this curved mirror surface perpendicular. If a light ray comes through this principal axis, it gets reflected back along the same path there because the concave mirror surface is touched by this principal axis perpendicularly. So in the same way, this convex lens also has this principal axis, in which what is this principal axis? The line joining the two center point of the two spheres which were used to make this convex lens. The line joining the two center point of the spheres which were used to make this convex lens is called the principal axis. And the principal axis runs through this convex lens in a way that it touches the curved surfaces perpendicularly. එතකොට මේ curved surface එක හැමතිස්සෙම මේ principal axis එක perpendicularly inset වෙලා තියෙන්නේ. If there was a light ray traveling through this convex lens along the principal axis, මොන දැන් මම ඔයාලට කියලා දුන්න තව law එකක් මීට කලින් එක මම කියලා දුන්නා. Refraction වෙනකොට, when you have a refraction, if this is air and if this is water, refraction එක වෙනකොට when there is a light ray touching the interference perpendicularly, no refraction takes place. Light rays just enter the second medium without a refraction. So the same thing applies here. Now in this case also, if there was a light ray to be traveled, along the principal axis එක ගිහිලා මේ curved surface එක touch කරන්නේ perpendicularly. එහෙනම් there will be no refraction take place. The light rays just enter the glass. Again the light ray tries to go away from the glass while touching the curved mirror surface perpendicularly. And there will be no refraction. Again the light ray enters without any refraction to the second medium. So this is what we have to understand. The principal axis of the convex lens is perpendicular to the convex lens. Principal axis is touching the curved surfaces of the convex lens perpendicularly. So if there was a light ray trying to go through the principal axis, there will be no refraction take place, but the light ray would enter into the glass without any refraction, any refraction, and then even into the second medium without any refraction. This is simply what happens, right? So did you understand that point? Was it clear? Vincent, right, okay. So Upe, can you just go through it as a briefing?
Yes, sir. The center of the sphere that forms the surface A is denoted as C2, and the center of the sphere that forms the surface B is denoted as C1.
So surface B and A is the things what I have marked with yellow and blue lines on the screen. Okay, right. Okay. Next part.
The line that joins these two centers, C1 and C2, is called the principal axis of the lens.
So this is what I was talking to you about. This is the principal axis, okay? That is perpendicular with both of these curved surfaces. So the light rays traveling through this principal axis would experience no refraction, but travels through them directly through it. Right, okay, next part.
At the points where the principal axis intersects with the surfaces of the lens, the principal axis is perpendicular to the surfaces. Therefore, a light ray that enters the lens along the principal axis will leave the lens without bending. The midpoint between two surfaces of the lens is called the optical center of the lens. Any light ray that travels through the optical center passes through the lens without any bending.
Right, I have to teach you what optical center is and center also, right? What it is, it's actually this. So if you can see here, can you see that this principal axis? And if you draw a line like this, in a way that the lens be very symmetrical, okay? The lens be very symmetrical, and the point where the symmetrical line of the lens meets the principal axis is called the optical center. That's called the optical center. So if there's any light ray tries to travel through the optical center, will also not subjected into refraction. So how do you obtain this optical center? You have the convex lens, you have the principal axis, and then if you draw a line to symmetrically divide this convex lens, that line incidence, that line actually intercept this perpendicular at a point called optical center. So if there was a light ray trying to go through this optical center at any direction, right? If there was a light ray trying to go through the optical center like this, no refraction. Light ray trying to go through the optical center like this, no refraction. Optical center there will be no refraction. That's what simply it is. Okay. Right. I will talk about that in detail. Let's move into the next part. So you have to understand what is the optical center. Optical center is the point. What is met when you try to divide the convex lens symmetrically into two. The point where the symmetrical line meets the principal axis is the optical center. Any light ray trying to travel through the optical center subjects into no refraction. Right. Okay. Right. Next part. Yeah. Convex lenses are converging lenses. Right. So for this, you have to draw a diagram like this. Keep it in your mind. This is very simple. So then these should not be much difficult things for you because grade 7 right? Okay. But we had to follow up some technical parts here. Right. So here you have the convex lens. All right. So convex lens, and then this is the principal axis. Okay, this is the optical center. Keep it in your mind. If you take like 2 centimeters to mark F, right? If you take like 2 centimeters to mark F, okay, focal point, right? That focal point, right? Me convex lens like optical center. From the optical center to the symmetry of the lens, if you take මොකක් හරි distance එකක් ගත්තොත් හිතන්නකෝ අපි ගත්තේ අනිත් මේ concave mirrors වලට 2 centimeters නේ. So consider that to be 2 centimeters මෙතනට. If you take this one to be focal point, ඒ වගේම length එකක් ගන්න ඕන 2 centimeters ගන්න ඕන 2f වලට. That is center of curvature. ඒ මොකක්ද? Hold on. Now there's this light ray එකක් එනවා, parallel light ray එකක් into this convex lens. Concave lens light ray, parallel light ray. The light ray gets converged and focused on the focal point. Another parallel light ray comes, gets converged and focused on the focal point. So since these parallel light rays are converged by this convex lens, we call these convex lenses as converging lenses. We call these convex lenses as converging lenses. So if you can remember this symmetrical line, can you remember the symmetrical line? From that line to the focal point, the distance is called focal length. That's called focal length. So you symbolize it with F, simple F. You symbolize it with simple F, right? what happens? There was this convex lens, and the parallel light rays comes, gets converged and focus on the focal point. This line which we drew to a symmetrical divide this lens into two, that is from that line, the length to this focal point is called the focal length. And if there was a light ray coming through principal axis, it would subject into no refraction but enters into the next medium immediately, right? Now, this focal point is just the focus point of this lens. Meaning parallel light ray account, light ray focus karane retina එක උඩට. Sorry, light ray focus වෙන්නේ focal point එක උඩට. Converge වෙලා focus වෙන්නේ focal point එක උඩට. But if you can you remember මේ lens එකේ මේ surface එක ගත්ත මෙන්න මේ lens එකේ මේ surface එක ගත්ත sphere එක මතකද? A sphere, if you had this sphere like මෙහෙම තිබ්බොත් ලොකුවට මේක තියෙනවනේ මෙහෙම ලොකුවට sphere එකක් තියෙනවනේ. A sphere එකේ center point එක තියෙන්නේ. A sphere එකේ center point එක is 2f. So 2f කියන තැන ඉඳලා තමයි radius එකක් කරන් අපි sphere එක ඇඳලා තිබ්බේ. A sphere එකේ curved surface එක තමයි මේක. And එතකොට the distance from your focal point to the center of curvature of this curved surface has to be also equal to distance from focal point to this symmetrical line, right? එහෙනම් මතක තියාගන්න අර කලින් lenses ගැන කතා කරාම වගේ තමයි 2 centimeters if it is here from here, this has also to be 2 centimeters, right? Okay, keep it in your mind and you can draw this diagram under convex lenses are converging lenses. Convex lenses are converging lenses. Keep it in your mind. මෙතනලා මෙතන 2 centimeters ගත්තා නම් මෙතනලා මෙතනට ගන්න ඕන 2 centimeters. Okay, right, go for it quickly. Upe, did you drop long ago?
No.
All right, okay, so then these are the things what you need to know. A parallel light ray, after getting refracted from the convex lens, bends towards the principal axis and travel through a single point on the principal axis, which is called the focal point or the focus. That's what we have marked as if, right? The distance from the optical center to the point, to the focal point, is called the focal length, right? So this was called the focal length, if you can remember, right? The distance from the optical center to the focus point is called the focal length, right? Next part. When ray diagrams are drawn, the focal point is denoted as capital F and the focal length is denoted by simple F. We know that from long ago, right? All right, so then we are trying, okay, see here, drawing ray diagrams for images formed by convex lenses. Size, nature, position of the image formed by convex lenses depends on the distance between the lens and the object, that we know, right? So if you draw the ray diagram properly, you could identify the shape, size, and even the position of the image formed, right? So same as before, if you could remember when we were doing this same thing with this concave and convex lenses, mirrors, we had the mirror surface, we had the principal axis, and then we had focal point, and we had 2f point. We kept the object in between the focal point and the mirror, and then on the focal point, in between the focal point and the 2f point, on 2f, and even beyond 2f. And then we just observe what would happen to the light rays come from the object to the convex to the mirrors, and how would they get reflected and the images be formed. So the same thing is done here as well. So before doing that, we need to know how the light rays behave when they're traveling through convex lenses. Okay, Upe, can you read me the Roman number 1, please, for me to draw the rules for you?
Yes, sir. If the light ray travels through the optical center, no refraction takes place.
Okay, number 1. Okay, so you have the convex lens like this, and convex lens like this. Hold on. If you have the convex lens like this, okay, and then you have the optical center like this, and light rays travel through the optical center. මෙහෙම යනවා, no refraction. මෙහෙම යනවා, no refraction. Hey, light rays are traveling through the optical center, no refraction take place, right? So you can quickly draw this. For number 1, I'll just give you time. Upe, for the second one, tell me.
If a light ray parallel to the principal axis comes to the convex lens, ray converges to at focus.
Okay, that's very simple again. So you have the convex lens. Principal axis is this. If this light ray travels parallel to the principal axis, if the light ray travel parallel to the principal axis, if the light ray travel parallel to the principal axis, the light ray goes to the focal point. It goes to the focal point, right? Now it gets refracted. It was to be traveled on this pathway. No, it has changed the direction of its travel, and then it has gone through the focal point. If the light ray reaches the convex lens parallel to the principal axis, the light ray get refracted and then travel through the focal point. So the next law has to be the reverse of this law, right? Isn't it, Rupe? The third one should say you have the convex lens, you have the principal axis. If there was a light ray, now you have the focal point here. If there was a light ray trying to reach the convex lens through the focal point, if this light ray try to reach the convex lens through the focal point, the light ray should get refracted and travels parallel to the principal axis. Then මේකේ මොකද්ද කිව්වේ principal axis එකට parallel light ray එකක් ආවොත් refract වෙලා principal axis එකේ තියෙන focal point එක through යනවා. ඒකම reverse එක focal point එක through ආවොත් refract වෙලා principal axis එකට parallel. If the light ray reaches the convex lens through the focal point of the lens, the light ray gets refracted and travels parallel to the principal axis. Oh, මේ lens එකේ දෙපැත්තෙම focal points තියෙනවා. ඒ කියන්නේ optical center එකෙන් දුර 1-2 cm මේ පැත්තේ focal point නම් මෙතනලා 2 cm වලින් තියෙන මේ පැත්තේ focal point. මෙහා පැත්තට 4 cm ගියපුවම 2f නැත්නම් center of curvature නම් මෙහා පැත්තට 2 cm 4 cm ගියපුවම ආයෙ center of curvature එකක් තියෙනවා. ඒ කියන්නේ දෙපැත්තෙම තියෙනවා f and 2f. Right. These are the three laws. Quickly you can note it down. Okay, the next situation. Now we are going to keep the object in front of the convex lens and then see how would the image be formed, right? So in the first situation, you're going to keep the object in between the convex lens and the focal point. Okay, so then see how it goes. Okay, right? We have the convex lens like this, and then we have the principal axis. Okay, right? And then we have the optical center here, the focal point here, and the 2f here. මේවා equal distances වලින් ගන්න නැත්නම් වැඩේ ඔක්කොම අවුල්ලා, right? And then we place the object in between the focal point and the focal point එකයි lens එකයි මැද්දෙන් object එක place කරනවා. Right? This is how we place the object. Right. Now see what will happen, right? Object එකේ ඉඳලා එක light ray එකක් reaches the convex lens like this. Hold on. Yeah. ඔක අනිත් පැත්තට ගමු. So then අවත් බැලේ මොකද උනේ කියලා අපි සාමාන්‍යයෙන් අඳින්න ලේසි පැත්තට ගමු. නැත්නම් හින වතයක්. ඔක අඳින්න ගියා. So it's like this අනිත් පැත්තට ගමු, right? Then it will be easy for us to do. මොකද අපිට හුරු පැත්ත එකනේ වන්දලේ මොකද උනේ කියලා. Right? Convex lens, principal axis. I'll take this as the optical center. This is the focal point. The length has to be equal to the center of curvature. එක ගන්න අනිවාර්යෙන් දශමයක්වත් එහෙට මෙහෙට වෙන්න බෑ. හැමුණොත් වැඩේ නානවා. හරියටම values ගන්න. Right? Then I have this object placed in between the focal point of the lens and the lens. Focal point and the lens. ඒක මැද්දේ තියෙන. Focal point එක lens එක මැද්දේ තියෙන. From the object, there is this light ray traveling to the convex lens, and එයාට මොකද වෙන්නේ? එයා refract වෙනවා through the focal point. The focal point එක through refract වෙනවා. Right? Object එකේ ඉඳලා parallel light ray එකක් යනවා lens එකට, light ray එක refract වෙනවා focal point එක through. Right? Got refracted. දෙවෙනි light ray එක මොකද වෙන්නේ? object එකේ ඉඳලා optical center එක through යනවා. Refraction එකක් වෙන්නේ නැහැ. So මෙහි ඉඳලා තමයි අපි object එක දිහා බලන් ඉන්නේ. අපි මෙහි ඉඳලා object එක through lens එක through object එක දිහා බලුවා, right? From this side, when we look into this object through the lens, we see that the image is formed on this side. Okay? So in this situation, the object is placed in between the lens and the focal point. First light from the object reaches the convex lens parallel to the principal axis. The light ray gets refracted through the focal point. Second light ray from the object comes through the optical center to the eye. So we see this object through the lens on the other side of the object is on the other side. So we see the object through the lens. So the image will be formed on this side. How the image is formed? We have to extend the two light rays. We have to extend the two parallel rays. Okay. So if you extend the two parallel rays, the place where the two extensions meet, there will be an image. Right? You can't specifically tell where the image is formed. It's in between F2F or on 2F or beyond the 2F. You don't want to mention that, but you can mention like this. What sort of an image is that? You can't take that image onto a screen because image is on the same side of the object, right? So you can't take that image onto a screen. So it's a virtual image. It's a virtual image. You can see that clearly, right? So second thing, what do we, when we are describing about the features of the images, what is the second thing that we do? Upe, quickly, can you tell me? We say the virtual or reality of the image, and the next one is the size. Upe, what is the second feature? Quickly go to mirrors and tell. Upeka. Hello, Lamai, are you with me? Lamai, can you hear me?
Yes, sir.
Upeka, are you there? Emily, can you tell me the second feature that we look into? Virtual image, and what is the second feature? Is it the size or the orientation? I just need the order.
Orientation.
Sure, the virtual it was orientation the කියන්නේ. Size තෙමේද? නෑ අපි ලියලා තියෙන්නේ මොන order එකකටද? එමලි ගාව තියෙනවද ලියප එක?
Oh, sir.
හරි. Then orientation. So what would be the orientation? The orientation of the object and the image is the same. They are upright, isn't it? Upright. And then size Emily.
Oh, sir.
Yeah, object size and the image size. The image is magnified. So image is magnified. It's a magnified image. And the position of the image formed on the same side of the object. Image is formed on the same side of the image. Same side of the object. Okay. So the final thing, what can you say about the object distance and the image distance? Image distance is greater than the object distance. So you can write the next one. Image distance is greater than the object distance. All right, you can quickly draw it. Iliwa, you know other? If you can remember the second situation, this is the second situation. If you can remember the second situation, says you to take the object behind a little. So earlier, this is the optical center. That principal axis has to the optical center. This is focal point. If it was 2 centimeters, this is 2F, which is a center of curvature. Now they say us to take the object up. Earlier, the object was placed in between the focal point and the lens. Now they say us to take the object onto the focal point. We have taken the object back. Okay. So from the object again, a light ray travels parallel to the principal axis, gets refracted. Keep it in mind, if this was 2 centimeters, the distance from the optical center to the next focal point will be also 2 centimeters. So if there was a light ray traveling from the principal axis, hold on. Right, focal point is this, right? If there was a light ray traveling from the object to the convex lens parallel to the principal axis, the light ray gets refracted. Sorry, the light ray gets refracted and travel through the focal point. And the second situation, second light ray goes to the optical center. Second light ray goes to the optical center, no refraction takes place. So if you could see here, you're looking at the object from here. If you could see here, these two light rays are parallel to each other. So they would never meet, isn't it? They would assume to be meet at the infinity. So we assume that the image forms at infinity. Image forms at infinity. So we can't tell anything about the image which forms at infinity. Know any other details about it. So what simply happens when you take the object onto the focal point of the convex lens, one light ray reaches the convex lens parallel to the principal axis, it gets refracted, goes through focal point on the principal axis. Second light ray directly goes through the optical center, subjects into no refraction, and we are looking through the lens into the object from here. The image appears to be blurred actually because why? These two light rays are parallel to each other, so they will be meeting. We assume them to meet at infinity. So then these two light rays will meet at infinity, so the image will be forming at infinity. So we can't talk about any features about an image which forms at infinity. So we have no any idea. Actually, in this situation, what really happens? The image becomes blur, right? In the practical situation, the image becomes blur, nothing else. Write it. Draw it here for here, right? When the object is on the focal point. Right, on Monday we can finish this lesson and then we will jump into the waves also. I'll share the waves thing also with you, and then you can do the what do you call while you're